Welcome to NITK CIS's talk on fundamentals of CNN and design practices for computer vision. During the course of this talk, we will be discussing some of the more deeper details of CNN or how computer vision works on the whole. And before we begin, I'd like to introduce our speaker for today. Conv2D is currently research fellow at the Stanford University School of Medicine, where he is currently working on his software specially designed for preclinical 3D biomedical image processing, archiving, translation, and segmentation. He has also previously served as a senior computer vision engineer at OpenCV, where he's worked on ADAS systems for autonomous vehicle vision LiDAR and multiple projects based on small detection on satellite imaging, advanced facial recognition, as well as anti-spoofing technologies. He is also an awardee of the TIF AAC Award at ISC Bangalore, where he received for his work on advanced ADC recognition for process technology. So without further ado, we'll get on the session and a round of applause.
Alright, it's good to be here. Good evening. My name is Karnataka. I am a research fellow at Stanford University School of Medicine. I'm also an active member of the CBF Computer Vision Foundation. Right. Welcome to this guest lecture on fundamentals of convolutional neural networks and design practices for computer vision. So let me quickly show you the agenda that is planned for today. Right. So we'll actually start with an introduction to deep learning. Right. We'll kind of unlearn and relearn. Right. So we'll start with that, and then we'll talk a little bit about the components of convolutional neural networks. And in this specific part of the talk, I'll be talking about various components of the CNN, where to use them, how to use them, and how to kind of position them in the network to get the best possible results. Okay. The third thing is that now you learn all the components of the CNN. And then what the design practices that you can follow to get the best possible result. Especially if you are trying to build state-of-the-art models, or if you're trying to train on these models for a specific use case, how to do that and what's the intuition behind doing what you're supposed to do. And in the end, we'll also have an end-to-end model training pipeline, which we will do a hands-on session using PyTorch. And we'll try to train the image classification model for stage. We'll build the model, we'll also train it, and we'll also get the results out of it, and we'll check how well it works. Okay. Does that sound interesting?
Yes.
Alright. So before we go into the lecture today, this is actually what I'm actually working on right now. So on the screen, you can see that I'm actually working on early detection of cancer cells. Over here, specifically on PET-CT imaging. Okay, so PET-CT is actually 3D imaging technology which we use to perform some kind of organ segmentation on small animals as well as human beings. Okay, but what you're seeing on the screen is not human beings; these are lab rats. Okay, so there are actually 4 lab rats over here. So you will have to do a complete scan of this structure based on different experiments, and then segment out organs from this data, and then kind of perform some kind of analysis of it to get valuable results. And this is specifically for early detection of cancers. And the work that we've done so far was also published in WNYC 2024 Canada. WNYC stands for World Molecular Imaging Congress. Okay, and so alright, so what have I worked on in the past? So I was actually serving as a senior computer vision engineer at OpenCV, where I was also involved in the research and development for ADAS systems, specifically for autonomous vehicles. Okay. So on the screen, you can see that this is actually using stereo vision, using this model called a stereo transform, or an STDR. Okay. So what it does is that it takes 2 inputs, like for example, there are 2 cameras in the car itself, and it uses that to perform character recognition. Okay. So it's similar to the human way of perceiving character as well. So let's do a small quick exercise. Just take your index finger, keep it in front of you. right? I want to close your left eye and look at the tip of your finger, right? Don't move your hand, right? Just look at the tip of your finger, right? Now just imaging to that, right? Close the next eye and open the other. Okay. So what do you observe? It's understood, right? So the study was a parallax. So it turns out that using that, the brain kind of tricks itself to perceive depth. So this is like a human-centric approach that I would tell to perform real-time testing. And you can see that in real time, there are some parts moving. I'm not sure if it's visible over here, but actually there are waves moving. There are trees on the right. There are cars on the left. Is that visible? Actually, yeah. Right. So the other thing is parallel. Right? So when you close one eye, there is some part of the scene that you can't see. Right? But on the other hand, when you can change your eye, there is again some part of the scene that you can see, and there is some part that you cannot see. Right? This is again the same thing. So when you use stereo vision, there are some parts which the model cannot see. Right? So this is the disparity map that the model is able to generate based on the stereo inputs. Okay, so the next thing is a little bit of sensor fusion, right? So you have a 3D LiDAR component on top of the stereo vision component itself. Right? So why do we do that? Right? So the thing is, sometimes there is a variation in weather conditions. Right? So especially in the US or in the UK, you have snows, you have haze, you also have a lot of weather conditions which do not let the car navigate during night times. And especially what if all of this happens together? It's very hard for the car or the vehicle to navigate. So what we do is we can bring a mapping component over here, which will kind of do a three-dimensional mapping of the scene which is around this vehicle. Then you fuse that with the stereo vision component that you already have to get the better mapping abilities in terms of perception. Okay. So what you can see over here is that this is happening in Pune, right? So this is from the Canada itself, but you can notice that the bounding boxes are three-dimensional. Okay. And how do we do that? We do that using the 3D LiDAR component. And this is actually the bird's eye view or the P2P of that specific scene. So you can see that it's moving in the aspect. And this is actually possible using this model called KFPN. And KFPN stands for Key-Point Feature Pyramid Networks. Right? So you use this model to kind of fuse the 3D LiDAR size as well as the two-dimensional bounding box coordinates that you get from the camera. Alright, so with that, I'd like to start with a little bit of introduction to deep learning. Okay? I'm pretty sure that you would have had some kind of exposure to deep learning and some of the definitions that you might have learned during some of your courses that you might have taken in the past. But I tend to follow a human-centric approach and try to give a different perspective to what we. Alright, so this is actually a newborn baby, right? So the baby does not know anything, right? It's just born and it's introduced into an environment for the first time, right? And it's learning to do random things, right? It's not aware of its capabilities just yet, but it's kind of moving in the space and trying to learn the most, right? But what happens is that the mother is actually the first person that teaches few different things to the baby. For example, the mother actually points to the father and says that, hey, this is your father, right? And the first time the baby learns to recognize two people who live very closely with the baby, right? So it learns to differentiate between these two people, but it knows them and it recognizes them, right? But as days passes by, the baby learns to crawl on its own, even though the parents did not teach how to crawl, or they did not demonstrate to crawl, right? But the baby does that on its own, right? So, yeah, it is really fast also sometimes. If you don't monitor the kid, right, this might also happen. Right? And then the baby actually starts to take small steps and learns how to walk on its own, because it's actually starting to look at people around it, and it's also trying to mimic those actions, right? And then finally, these are the first proper steps that the baby was able to do. And I think it's the most precious moment for the parents themselves to see their baby learn and learn to walk on YouTube. So the question now is, how are humans capable of learning? Right? So these are very important questions. And it turns out that the human brain is one of the most complex and sophisticated organs in the human body. Okay? So it turns out that there are approximately 100 billion neurons which are present in the human brain. Okay? We're not probably using everything, 25% of it. Okay? But the brain is actually developed and built in such a way. And this is actually the neuron, right? So it's actually called a neuron or a neuron within the brain. Okay? I'm pretty sure that in your, let's say, 10th or 11th grade, if you're taking a biology stream, then you will have to look at each neuron. Okay? So you have the cell body, you have the dendrite, you have the nucleus, you have the axon, and the axon. And based on the input stimuli that the neuron receives, it kind of decides whether to fire up that neuron. So now the question changes a little bit. Can you artificially design a brain? So it turns out you can. So the idea, the Buzzard model, over here, the mathematical model, was first designed by Frank Rosenblatt. Right? And this was actually in 1958. Right? It's probably 66 years ago. Right? And this was the mathematical model of the Buzzard model here. So if you notice, there is actually inputs over here. Then you also have weights. So you have W1, W2, W3, W4 for each of these input components. Right? Then you also have a little bit of summation and noise. So this is where the weights and the inputs they get summed up, and you also have a noise term over here. And then you have an activation function. Okay? So this activation function actually decides whether the output from this perceptron goes to the next neuron or not. Okay? So you have like a filtering mechanism over here, and based on the activation function, you decide whether to activate or not. So, you will notice the similarity. Right? So this is actually the human-centric component that I was talking about. You have the nucleus cell as well as the perceptron here, which looks very similar. So then, if I had to manually or formally define deep learning, then it would be something like this. Okay? So it's actually a subset of machine learning that utilizes neural networks with multiple layers to be able to capture complex features or complex patterns from the data that are given as an input. Okay? So this is how you would formally define deep learning. So with that, I'd like to move on to the next part of this lecture, which actually talks about the components of convolutional neural networks. Right? So let's go. So over here, before we start trying to looking at the model itself, you need to understand what is the format of the input data that these kind of models would have to use to do some kind of processing. So this is actually how an image will be perceived by a computer system. Okay, so it's actually a grayscale image, which means we just have black and white pixels. Okay, so you can see that images actually appear as pixels, right? And they're actually digitally represented as two-dimensional pixels. Okay, I'm not sure if it's visible, but you can see that each of these pixel components they have a value within it. So there is actually a range for these pixels as well. So 0 to 255. So that's the range. So 0 actually represents the most darkest or blackest pixel near image. On the other hand, 255 actually represents the whitest or brightest pixel from your image. And everything that comes between that follows a different range, which you can stay with. And this is the two-dimensional matrix that you get over here you remove the code. And what's the purpose of developing NITs? So the purpose is kind of split into two stages. The first one is to perform feature extraction, right? And the second part is to use the features that you've extracted and do some kind of classification based on the features that you have. And let us start with two-dimensional convolutions over here. Right? So you can see that you have a kernel, and a kernel is nothing but a small matrix of waves. Right? So this moving window over here is a kernel. Right? And over here, when I'm actually talking the laser nodes, you can see that the kernel has three values within each of these components. Okay. So what happens is that it slides over the two-dimensional input data that you have, and it performs element-wise multiplication on each slide that it does. Okay. So you can see that as and when it slides, there is also a new output filter which is getting formed. And if you see this and this, these are the final outputs that you get out of the and this would actually result in a single output exchange for each Conv operation. You have a single output value that is. Okay. So this is how your two-dimensional convolutions work. But trying to just note this is not enough. Okay. So let's take a step further and dive deeper into pattern. So what happens is, let's say that I have an input matrix, right? So I think this is a 5 cross 5 matrix, okay? And what if I want the resultant output feature to also be a 5 cross 5 matrix, okay? So I will introduce padding component, in the border of the 5 cross 5 original input matrix, right? And on that, I perform the same Conv operation, and then what happens is have the same size as well as the output feature filter that you get out of the convolution. So I believe what we want is that sometimes you need the size of the input to build the output feature, right? And this is how we do that. And if you do not do this, then what happens is the edges will get eaten off. Okay? So if you want to avoid that, then padding is the first implementation that you use to get the best feature in the So over here, the original pixels are placed in the center, like I just told, and the padding is beyond the edges. This is what we do, and the value is done using zero value, which means these are zero mixing value components. So we learned that we learned how to use CNNs, for example, on operation. We also learned the value component. So the next component is actually called sliding. So we said that the filter, the Conv filter moves like sliding window approach. Right? But what if we want to kind of decide how well or how much the length of the movement of that specific filter? And for this, we can actually use something called striding. You can see that the idea here is to skip some slide location on the kernel. Right? So it's not like you're in one slides, but instead of that, you're trying to let's say you're skipping 2 slides, and that means like stride of 2. So you have over here is that stride of 2 means skipping slides 2 pixels off. Okay? And therefore you have a downsized component roughly by the factor of 2. And this would be your output feature if you increase the stride. And this is also called as stride length, right? Or stride length. So what happens if we use striding and padding together? So let's look at the first example over here. You're doing a Conv operation, but you're using a stride of 1 and padding 0. Okay. So you can see that it's moving every single stride, right? But we don't have any padding. So then what happens is that for each filter, you get 1 resultant output, and this is how that output filter will be formed. But on the other hand, if you use stride 1 and padding 1, You also, introduce a valid component around your input feature, okay, feature matrix, okay, and you now actually changes, okay, because you have an external component. You also choose right over and then get your final feature. This is another example. That using stride of 2 and padding 0. Okay. So now we just have a 2 cross 2 output feature from this 5 plus 5 output feature. And on the other hand, we have stride 2 padding 1, and this would be the resultant component to the introduction padding. But till now, we were just considering grayscale images, right? Which means it has just one channel. But the images that you know and see every day are RGB images, which means they have 3 channels. Okay? And this is how it would look if you try to split the channels. Okay? So this is an RGB image of 3 possible here, and this is the red channel, this is the green channel, and this is actually the blue channel. And only when you add all of these channels, you get this RGB image. And I know that some of you might think that this should actually look like red color, right? And over here sometimes it should look like green or it should look like blue, but it can't because we've not added the other 2 components. And you can make this look red if you add 2 zero bases for green and blue, right? So then this will look red, this will look green, and this will look. Each of the kernels of the filter slides over the respective input channels, right? And it will also have a process version of each. So over here for each channel. And then what happens is that you have again the collection of kernels, and for each of the word process versions, it's finally something into one final channel. Okay? And you take this channel and you add a bias component, right? A bias kernel to produce the final output channel. Right? You have the final output channel. And you take that and do further processing. Alright, so the next type of layers that I'd like to talk about are known as pooling layers. Right? So there are actually 2 types over here. So on the left, we have max pooling. Right? So for each slide, the maximum value within that component is actually taken as an output over here, the max values. Okay. So in this, you have cell, okay? You have cell over here. In this component, you have 3, so 3 comes here. So over here, you have 9, so 9 comes here. And over here, you have 3, so 3 comes here. So this is max pooling. And on the other hand, as the name suggests, you have average pooling, which means it takes the average of that component and it takes that as an input and just gives out the average values. But how do you decide when to use max pooling and when to use average pooling? Okay. So let's have a look at that. So what happens is max pooling actually extracts the most salient features in that specific feature matrix that you have. Okay? Those are the feature map. And what happens is that when you set the maximum value within that component, you get a spatial invariant representation of the complete feature map. Okay? And what happens in average pooling is that when you compute the average values over here, while doing the pooling operation, you get sample feature maps. Right? So you're trying to sample the feature map as well as trying to reduce spatial dimensionality within your data. Right? When you try to move across different components in your data, especially when you're trying to go much deeper into deep CNNs. And this actually helps you to preserve important information, right? And this will happen in a much more uniform manner. Alright. So we did talk about activation functions, right? But as part of this lecture, I was going much deeper into each activation function and when to use them. So you can see that there are multiple activation functions on this page over here. And if you just do a quick Google search, then you would get the specific research paper which introduced these activation functions. And that will actually give you a better understanding on where you use which kind of activation function, for which task you choose which kind of activation function. What happens is, on a general rule of thumb, for binary classification is problems, we use sigmoid activation function. Let's say that you want an output of 1 or 0, right? Cat or dog, right? So we use a sigmoid activation function. But on the other hand, if your data set has multiple classes, right? So let's say cars, persons, trucks, things, everything, all of that, you would want to use an activation function for that. So you use something called a softmax activation function. Okay. So for each class, you get a probability based on the input component that you forward pass in the CNN. So this is nothing but the activation function. Alright. So now you have to look at the feature extraction part. We've extracted the kind of features that we want to solve our specific problem. Now it only makes sense to use these features to perform some kind of classification. Okay. So let's have a look at that. Okay. So to do classification, the first component or the layer type that you might want to use are known as preliminary layers. Okay. So what happens over here is that for each layer over here, you have the input neurons over here, or you can call them as the input nodes as well. All of them are connected to the output node over here. Okay. So and this is how the mathematical representation actually looks like. Based on the input, the price, the weight, right? Then it gets added, the expression is different, right? And this would actually enable complex non-linear transformations, especially when you try to do feature extraction in the previous one. So when you add all of this, and when you bring all of these things together, the architecture of the CNN looks something like this. Right? So you have an input image, right? You have your feature learning stage, and then you have a classification stage, right? So these are like, let's say, 2 on blocks. So you have one on block with the relative activation function, and then you get some kind of coding to do some kind of dimensionality reduction, right? Let's say, and then you have stage 2, where you also have another form block, right? And then you have boolean. So now you've extracted your features, and now you pass that into classification block. Right? So what you actually do is you flatten this, right, into a one-dimensional representation, and you use that as an input to your fully connected layer component. And finally, you use a softmax activation function because let's assume that this data set has a lot of classes within it. So if you want to get the probability of this car, if it's really a car, and the other probabilities for the other classes. And this is what we will finally do. Okay. Not sure if that is visible again. Can you turn off these lights? The first one. Is it visible now? Can you all see it? Yeah, so you have an input image over here. It's actually a handwritten image. Okay. So these are for handwritten numbers, 0 to 9. Right? And it's a very famous data set called MNIST. Right? These are actually 28 pixel plus 28 pixel input images. Right? And you can see that the common blocks are doing their job, and this is actually doing inference. Right? It's not doing training. The model is already trained, but when you forward pass an input image of a handwritten number, it knows which node or which neuron to activate to get the final classification done. Okay. So this is how the visualization is working. Alright, so now we've had to look at deep learning. We've also had to look at the different components of a CNN, when to use them and when not to use them. Okay. And now what we do is that we have to look at some of the design practices that you might want to keep in mind when trying to design all of these CNN models from scratch. Okay. It will not just be for CNNs, but any kind of deep learning CNN model process. Okay. So let's have a look at that as well. So, how do you choose parameters for your two Conv layer and other layers. So that's a very important question. It's not that you start generating a thumb and then you layer. So the number of filters, how do you decide that? So actually what happens is the high number over here actually increases the network capacity. So if you have a lot number of these filters, it becomes a more deeper network. And it's more capable of capturing very complex features, especially if you have images in different classes which look very similar. So if you have, let's say, a car and the front of a truck might look somewhat different sometimes. Specifically, let's say a motorcycle and a bicycle also might sometimes look very similar. If you want to perform classification, common. So sometimes those are the cases where you need a very large, complex deep model. So that is when you increase the number of filters. But when you increase the number of filters, the computational cost for that specific model will also increase. So it's always good to start with a small number of filters and then gradually increase it if you want to go more deeper as well as capture complex features. So this is how you have to decide the number of filters. The second thing is actually the kernel size. So we saw that we are performing convolutional operations. So how do you define or decide the size of the kernel? So actually what happens is smaller kernels actually they capture local features. And what happens is larger kernels actually capture local features. Now, what do I mean by this? Let's say that we have a we have water. So let's see, let's have a look at here for a few minutes. Let's see that this is the input image, right? And let's see that I'm using this for, let's say, pathology, right? This is actually a pathology slide. And let's assume that there are a few cells over here, very small cells. Okay. So, so let's say that these are very small features over here. These are very small cells over here, and I would refer to this as local features. Okay. But sometimes what happens is that let's say that there is a structure over here which is part of the whole image. Okay. So what happens is this is a different structure. Okay. And when you use a smaller kernel size, so now let's say that this is your image. And of course this is an across 10 image. And usually all these sizes are very large. And you get kind of news, that this would be the resolution of this image. This is the greenhouses. So, for example, HD, full HD at home is 1920. So, this is the kind of computational complexity that you have to deal with in such a problem. So, what I was trying to say is that if I choose a 2 cross 2 kernel here, right? So, this would be 2 cross 2. Right. Then it works out. Right. I'm able to capture local features here. Right. So this works out. But what if I use the same 2 cross 2 kernel to also capture this whole structure? It might not really work. Right. So that is when you decide to go to a much more larger kernel size. So for this, you might want to go to a 3 cross 3 kernel, or depending on the size of the structures which are present in your slide, you can choose the best possible size of the So these are no dimensions. Okay. So this is how you would actually make the resistance, right? And sometimes what happens is you're using these libraries like NumPy, you can actually visualize the filter and the kind of features that it has extracted in the past. Okay. So you can use that to kind of do a trial and error method. You try to learn if your one layer is able to extract the kind of features that you want to extract or not. And based on that, you can play around with your results. Alright, so the next thing is stride, right? So typically what we use is that we use a stride length of 1, right? Because it moves across the entire image and we know that it's capturing good features. But a larger stride can also be used to reduce spatial dimensionality between areas. And again, padding, we usually start with the zero padding, right? One layer of zero padding around the input feature map. And based on that, you can also introduce more padding components. The input feature map would kind of match the output that you are getting. So this will help to maintain spatial dimensions. Alright. So, how do you optimize the number of layers and the number of parameters in your neural network model? So, the first thing is you have to do some kind of network simplification, right? So, let's say that you are training your CNN and you observe that it takes a lot of time for the model to train. Right? This can be a few reasons. One, you might not have the native GPU in your machine itself to accelerate deep learning training methods. Okay. So the second thing is, let's say that you are running it on an HPC with a GPU cluster of multiple GPUs, multiple NVIDIA CUDA accelerated GPUs, and it still takes a lot of time to train them. Okay. So that's because you have created a very large model, right? And sometimes it's good to reduce the number of layers, right? Specifically, in the network state. It doesn't mean that you have to have a very deep net. Okay? Sometimes a very small model would be enough to capture complex features from your application. So that is the statement that I made here as well, because not all problems require very deep neural networks. And then what happens is we can also start adding layers, right? Specifically if your model is underfitting on your data, right? Which means the model is not capable enough to capture more complex features from your input data. So that is when you would add layers, right? And you can also introduce techniques over here like dropout and fast optimization, which we might also explore. Alright. So, what is the approach to feature extraction? Okay, a specific design practice. So, what is the layer hierarchy? So, initially, the idea is that each layer, the early layers that you have in your network, should capture more basic features of the input that you give to the model. Okay? And when you go deeper into the neural network itself, you want to capture more complex features from the data that you have. Right? So this is very important because you can also do a little bit of trial and error by visualizing these layers. Right? And you can also understand the activations of each of these layers to know what kind of features are being extracted in each layer and is it being learned. And based on that, you can make a decision. And of course, cooling layers, we learned that you use it to reduce spatial dimensionality over here, and also you can enhance feature areas in your CNN. Alright, so what are some of my tips for design practices based on the experience that I've had in the past? The first thing is data optimization. So let's say that you are working in a research study and you have very minimal data available, very minimal raw data available to perform your study. Right? So what happens is you can't use very less data to train your models. So how do you train your model to be very accurate? So what happens is you can actually introduce photometric and geometric distortions into your dataset, the raw data that you have. And photometric is nothing but variations in brightness and contrast, right? Also, your sharpness and blurriness of your images, right? And geometric distortions are nothing but you're trying to flip them vertically and horizontally or along an angle theta. Okay? So you have a very wide range of components or more variance in your data set so that it helps better in terms of model convergence. The second thing is the learning rate. You want to use a learning rate scheduler, right? And this will help you to adjust the learning rate during training. Right? So if you have a really fast learning rate, then it means that your model might not learn more complex features. On the other hand, if you have a very low learning rate, right, it will take a very long time for your model to achieve convergence. Right? It might take more than 100 epochs for it to achieve its final perfect convergence. So it's good to find the best learning rate by using the learning rate scheduler to get the best value. And the last thing is, of course, experimentation, right? So CNN architectures, the design itself, it involves a lot of trial and error, right? It's not like you just take a pre-trained model from an interface, right? 3 lines of code and say, I'm a computation engineer, right? So that doesn't work out, right? So you need to design these models or know to develop architectures or novel model designs, and that only happens if you practice trial and error over here with a little bit of experimentation. So it's good to start small. And now we'll actually move to an end-to-end model training pipeline, right? Using PyTorch, right? So what I'm going to do is that let's do the hello world of computer vision, right? So let's build a CNN model from scratch to build an image classification model to work on the MNIST handwritten image data set. So these are black and white basically images, and they are in the size of 28 cross 28 pixels. Right? These are really small images. So you will try to build a model that will help us to do image classification. Right? So yeah, so let's do the hands-on session in using PyTorch. Let me quickly set up my environment over here. So what I want you guys to do is that just open up the browsers, go to Google Colab, right? And spin up a new GPU machine, okay? And we'll continue together. If you don't know how to do that, you can follow the screen. You have Google Colab set up, right? Just create a new photo, right? So how we do that is just the file and we get the screen. In this side is visual. Here I see video. That's why we video. It's fine. So what I do is choose runtime and change runtime type and choose your NVIDIA T40. Make sure to click that and then save, and then what you can do is you can connect it from here. Okay. So let's do that. And connect it. So now you have a CUDA has created GPU. You have NVIDIA speed for industry-grade GPU. Okay, so that, and if you use that to train a model. So what? So have you guys reached here? And everyone, opened up a new notebook. On still there? Is it open? Done? Okay. Anyone else? Okay, so open the notebook. Alright. So the first thing is to do some kind of encodes, right? And we'll do that for both PyTorch as well as the other libraries that we might want to use, right? So alright, so these are the eight main encodes that we want to use specifically for PyTorch library, right? So these are the few encodes that we want, right? So specifically torch.nl, it actually gives you access to neural network components like layers and all of that. Okay? So you can encode all the layers from this component. Okay? So element or functional, right? So this actually gives you more activation functions and other operations that you might want to use in your Python. And the torch.optim over here, right, actually brings in optimizers specifically for your model training pipeline, right? And torch vision actually gives you access to datasets, pre-made datasets in your training pipeline, which means you can directly import datasets which are already hosted somewhere by PyTorch, right? And you can use that to train your models. So these are three available days. And you can also do transforms in terms of augmentations, and it also has pre-trained models. So you might want to explore that sometime in the future. Then we also have torch summary. Okay? So once you build this scanner, let's say you want to look at layer-wise parameters for the entire neural network that you might have. Okay? And you can use torch summary over here to get the summary for that specific layer. Alright, after this, these are a few other helper libraries that you might want to import. Okay. So SQL or scikit-learn actually gives you visualization to check your convolution networks. Okay. So finally, if you want to see how well your model performs, you can use this to check the performance of your model and how well it works in terms of non-truth and predictions. Okay. NumPy, of course, is like an array calculation library. Okay. And MATLAB helps you plot the visualizations in terms of your graphs and all of that. And Steve also helps you with graphs. Okay. And finally, you also have TQDM. Okay. So if you want to introduce progress bars in your training pipeline and see how well it has been trained or how long it might take to install, then you can use TQDM. So do this and just run this step. You can use the play button, you can also use shift enter. So once that is done, you get a tick or a check mark on your code. Yes. Alright, so have we done it here? Have we included all the libraries? Still doing it? We'll give another minute for this. Right, we've done the reports. Alright. So now what we want to do is that we'll start building the CNN model itself. Okay. So if you used proofs, concepts on Python, then we use that as a defined neural network, specifically for CNS. So what we do is that we create a class, right? And we name it as a simple CNN. And start is n dot module. And here we have a new definition. Then we just use the code over here and pass your for CNN. And let's actually start with the first convolutional block. Okay. So I'll name it first on here. And what I want to do is that since all of these images are basically they have just one channel. Okay. So this layer will actually take one input channel. And since this is a base image. And let's say that I want to extract 32 output channels. And so when we talk about channel over here, so we mentioned that we specify that we have 32 output channels. Right? So what that means is that each filter will actually capture a different aspect or feature of that input. So then finally what it will give is that it will give 32 different feature maps. Okay. So that is what we try to mean by 32 channels over here. Okay. So this is that. And let's define this over here. Okay. So let's do a self dot on one. Okay. And you can use the NN module that we imported before. We have one input channel and 30 output channels. And we also have a kernel size. And we said that we can start with initial kernel size of 3. And I have a value of this. So this is how we would initialize the first convolution. And let's add another convolution layer over here. And over here, what I'm going to do is now I have 32 input channels from the previous operation. Right? So I'm taking that and I want to output 64 output channels now. The kernel says, let's say 3. Next, you can say conv2. and we can pass this here. Have we done it here? So as of now, we have two command blocks. So here what I want to do is add a tooling component, right? So we do a max tooling component of let's say 2 to 1, and we can do that saying that self.code over here, and you can get that from the module itself and say max to B, and you pass the so if you were to cross the max. Then, if I want to prevent a little bit of overfitting in my data model failure, okay. So then I can also bring in a dropout component in this data. Right. So for this, we can actually implement a dropout layer, right? So we can do something like this. Right. And let's say that is a dropout one. So you can get that from the NIT model itself. Usually, what we're trying to do is that once the force or the weight passes through this dropout layer, 25% of those weights will be dropped randomly. Okay. So this would kind of reduce the model's sensitivity to specific weights. So next, let's also implement a flattening layer, and this will be very simple. So self flatten, and you can get that from the NIT module. And once we flatten the input vector, it only makes sense to pass it to fully connected layers for classification. Okay. So let's implement that as well. So I do something like this over here for the first application here. We can just use you can make that as you want, and you can import it from the NN module itself, and it's called media. And this is what I will pass as your inputs as your parameters to this specific component. I'll also explain why we are doing this. So what happens is, so before reaching this final fully connected layer, right? So the previous feature map, okay, the feature map from the previous layer, from all of the convolution, the pruning, the dropout, all of that gets flattened into a 1D tensor, right? So when it passes through the flattened layer. And what happens after that is that that is given as an input to the fully connected layers. And this specific layer, the FC1 layer, actually, it takes the flattened input. Okay. So now we have 64 plus 64 plus 40 plus 40 over here, and that will give you somewhere around 12,544 features or something when you reduce it finally 128 inputs. Okay. So this whole thing, the whole number of features will be reduced to 128 final features. And the question here is, how did we get that 14 cross 14? And it will make sense because once you start applying the pooling operation, the conv operation, the pooling operation, and then the conv operation, that will be the final size of your output feature that you will get. Right? From the original 28 cross 28 MNIST image into MNIST. Okay. So initially the input image it has a size of 28 plus 28. Okay. And once it passes through the first conv layer, okay, it's actually 3 plus 3 layer. Okay. And we also added a padding of 1. Okay. So once it does that, you will get the same final output because we are preserving the same dimensionality. So the first output would be 28 cross 28. Okay. But after this, we are also doing a 2 cross 2 max pooling operation. Okay. And we also know that the stride of 2 is updated. Okay. So which means the dimensionality has again reduced from that 28 cross 20. Okay. And that has been done by half. Okay. Dimensionality has been reduced by half, and that is how we got the final 14 plus 14 component. And the second convolution layer actually maintaining the same dimensionality, so there is no changes in 14 plus 4. Okay, so this is how we would look at this thing. Alright, so let's also have another dropout. Okay, so let's make another. So I'll name this as dropout part. I'm creating a dropout here. But I want to increase the dropout percentage. I mean, and finally, I want one fully connected here. Okay. So I'll name this 1. And I'll create a new fully connected layer for the final classification operation. FC2. And what I would do here is that I'm only getting 128 features from the previous output. So I read that and include. And what I also output are 10 classes because the MNIST has just 10 classes. It starts from 0 to 9, which means it have 10 classes. So make that section. And just like that, you have defined all the layers that you might use in your neural network. And let's finally define the flow of waves in these layers, right? And let's close this. So we can create a new function and you pass this. and we'll actually define the flow of rates. So we'll start with this x, and let's say that I want to use a rate application function over here. And what I want to pass to this is the self.con1, right? And x will value the Next, what I want to do is I want to introduce the pooling operation as well. Okay, so let's do that. And I'll pass the second on. And now I'm going to introduce the dropout mechanism. Okay, so I'll do the dropout right here. And remember that we have two types of dropouts. The first one was 25%, and the second one was 50%. Okay, so the first one would be the 25%. So then what I want to do is dial this. Okay, so let's dial that. After this, I have my fully connected readers. Okay, so let's define them as well. Okay, and remember we have another dropout layer with 50% of dropout. So let's introduce that. And we name it as dropout. And pass next. And finally, we have our classification component, the final 10 class classification using your fully connected data. And it is return this. That's it. So this is a full definition of your class to build this simple scale. Now you can run this and you define that class. Has everyone followed it here? I'll keep it here for another few minutes if you are still following it. You guys able to follow? Clear? Yes. Still following? Yes. Yeah. The limits of value that happens. Yeah, so basically what happens is you have a flow of waves through each component of your other components. Okay, so let's say that there are 10 waves which are coming out previously. And what if I apply a dropout of 50%? And randomly, 50% of the waves from the previous input would be dropped off. What's the use of yeah, so especially what happens is finally you want to reduce the dimensionality. So we have the marker over here. Okay, so let's say we have multiple components. Okay, the cell and the right is components in your CNI. Does this make sense? So what I'm trying to show is that we have multiple controls in your neural network itself, especially to the CNN, right? And you can also, I've showed a illustration where the size of the control increases the image level, this kernel size. And when you keep increasing the kernel size, you're making this into a much more deeper neural network. And what happens naturally is that the increase of weights and each of them, and this keeps multiplying them. And by the time we go to the classification component, we also learn that the fully connected data, so for each input component, it's connected to each output. Each one of this is that similarly. And what happens over here is that the complexity of operations over here is very high. It's drastically, especially when you want to model that mathematically in equations and get parameters. Right? So that's why we introduce this dropout over here itself to gradually reduce the number of things. Right? By the time it reaches here, it has a number of weights or a limited component of weights which you can handle to do the final classification. Because we also learned that we are trying to convert a 128 component into 10. Okay. You have 128 feature points over here, right? 128, okay? And you convert that into 10. And we've already done that previously with something close to 10,000. So it only makes sense to drop out some of these weights and then progress further. And you would not do this, directly, saying that I will just start with 75% dropout directly instead of splitting it into 25 to 50. So you do a gradual reduction in dropout function. And by the time it comes over here, you have enough number of weights which you have to handle. So this is the mathematical implication that you might want to. So it is the how that's all right. It's for both. Okay. So now what we do is we also visualize this model and see how it looks. Okay. So you just okay. So the first line is very important because it checks the full accelerated environment if there is a GPU device available. Right? Most of you have faced this issue. Right? I think you install PyTorch and then but it does not use detect GPU that you have in a machine sometimes. Right? And when you face these kind of issues in the local environment, it really makes sense to use a virtualization package like Anaconda to create a virtual environment, configure your CUDN and put the drivers, and then install PyTorch and TensorFlow. And this will help you to, this will help your framework to detect your good accelerated GPU in your environment. Right. So the first time it actually checks if CUDA is available, and if it's not, then it leaves the CPU. And then we're getting into the sense of this model over here, right? And we're sending it to the device. The device is the GPU, right? And I'm also checking the summary where I'm passing the model as an input. And then what I'm going to do is that I'm going to sample input to the summary component here to check how well the model is in terms of the application. Noticing that. I go over here. Turning again, you see your display over here. This is one of the things we check that it says data. The questions, right? Are you able to notice this? So here what you do is that you have to look at the model architecture itself. So we also saw that the architecture itself had a summary component where you take the input model, take the model, pass a specific input, and check the layer-wise architecture and what that will scheme. So this is how it will look like. And you have the parameters. So now what I'm going to do is define the dataset and check the transforms that I want to use for this training paradigm. Okay. So what I do is do that here. Right. So you can define some transforms over here, right? So let's quickly do that. And we use using the transform.compose method. Ask the transforms like this. Okay, so first what we do is we'll try to convert it to tensors. And this is something that the architecture can really be processed. And we also do a normalization because we are actually using single channel variables. So let's do that. And I'll also explain all of this. So what we also do is we try to create data models. Right? So data models are nothing but the components that hold the part of a data set to perform training, in a training pipeline. Right? So we'll do that now. We'll split this as two data sets. So one for the train and one for testing. So train data set. And you can do something like this. And this is the MNIST data set that we can get from the transmission of the data. And we can pass the where you want this to get downloaded to your machine. So and you want to use this for training? Yes. Alright. Do you want to download this? Yes. Do you want to download this? And also, what kind of transformations do I need to apply on this part? Get that. And we'll apply the transformations that we created. And some of these here would be for the test data set. So you want to use the training mode. And I don't want to apply transformation to use. Optimization is required. And now we create the data elements. Okay, so let's name it as train and test rules. Right, so it has and you pass the train data set to this. And over here, I also have to mention the batch size. So which means for a single instance of the training pipeline, how many numbers of images will be there in that specific batch. Right? So let's also mention the batch size. Okay. So you also have that as the number of batch sizes. Okay. And you also want to randomly shuffle data per batch. So do that as well. So I want to say that, hey, yes, shuffle this. And what I want to do is update our test testing part. And so the data set I pass the test data set. And I don't want to stop this, it's not really. So we still have to download the data set. Let's keep this here for 2 more minutes. So now that you downloaded your data set, created data lookups for training and testing, you want to see how they use to play. Right? I'll just give some snippets over here, which will kind of visualize the images that you have in your data lookup, and you use that to see how they use. So you just start by looking at the images, right? And you do that in the idea and then here. And you can pass the training over the video. And all of these images, they also have labels, right? And what you do is pass that. So what this does is that what we're doing is we're trying to get all these values of ranges of the data that we have, and we pass them over here and use that to produce some kind of visualization CDUs. And for this we use MATLAB. Right? So we're going to use small function over here, but I am sure. Okay. And you pass your image. And what we do is we normalize the image. Okay. So previously we saw that we did a little bit of normalization as part of the transformation, but that will not be visible to human eyes as the way it's supposed to look like. So we have to unnormalize the data to artificially normalize. We do that. And we're going to do that in a unfile image because MATLAB works really well on unfile as an image. And we just using the BLE.IMShow function within MATLAB, which will output define image on screen. So we're using BLE.IMShow and we also transpose the values, right, so that it can get displayed on the screen. We also need to, I think this is transpose function over here, so you can be our transpose. Pass this directly. Okay. So we made a 5+5 array over here to visualize the image. Okay, so you say this function over here in MATLAB itself, where you consider the slide interface. And you also take a unit, right? So you call that function. And there is actually a method within the automation which will help you to make a unit, right? So you can use this we import it from this and it's called make. So what you pass is the 25 unit. And the number of rows over here would be like this. And just give a image. This image is great. So I did a small error over here. It's not NT dot, it's NT image. Right? We are passing this over here. And this is how the data set has changed. So we have to follow till here. Can we move forward to the training pipeline? First we need to create two instances. The first one is for the loss that you might want to use this specific use case. And the second thing is you also need an optimizer to optimize the capacity. So let's actually do that. Right. So the first thing that we want to do is define the loss, and we can name that as a training route. And this will actually go to web. And we can import this from loss and looking loss. Actually, we can be processing the loss. Also, identifying the optimizer. This will actually define the learning rate also. And you're passing that as an add-on optimizer. And specifically, in add optimization, it's actually an algorithm which kind of adjusts the learning rate for each training epoch that we might have, model training pipeline. Okay, so this will directly link the handler. So we can directly use that as a algorithm for us. And still, you are just passing the learning rate. And also, we can choose the number of epochs, how many training cycles do you want to train this model for. So start with 10 because it's a very small data set and it's a small model. It might converge really fast. Right? So we can use that. And from here, we can start to finish the training cycle. Right? So we can just mention this. For each of your epoch, we have really done all the steps of operations that you might want to do to train the model. Right? So we can just do for epoch in range, and then you pass the number of epochs. And then you put your model in a training. Okay? So you just say model or training. And also you can define a variable to hold the running loss across all of these units. Okay, we'll set that. And we also imported TPM to hold the progress of our training plan. So what we can do is we can use TPM system to create progress bars. What I want to do is pass my training order because I want to use that to train my model. Okay. And I want to create a hash. Yes. And from here is where actual training pipeline starts. For images and labels in your keyboard. What I want to do is forward pass those fields. So what I want to do is first I create a description for my DQ and progress manager, and then we'll try to define the model, the weight. So what I do is I'll create a description over here, and we'll use this method, set underscore description, and pass the name this. For each block, it's import the number of key blocks. And let's do it for each block. Okay. And what I want to do is I want to transfer both the images and labels to my device. Right? The device is the GPU over here. Right? So what I do is images and labels, right? And I'll pass that as well as my labels. And I'll initialize my hopping as well. And we also want the outputs. And we pass that. So what we pass the images. And we're also updating the loss real time. So what would be the criteria for that? We define the criteria on the previous two, right? So that will be the outputs. And the labels. We use that to calculate the list. And we also use something as backward propagation. And we create a new step in the object. So we create a new step. And we also want to update the real loss. That we are computing every record. So we can use 2 plus okay. And we also want to update the progress bar that we have each line for each block. Okay, so how to do that? We'll do something like this. And you pass your running loss over here as an input. And you give that, of course, to your training data model. And you take the length of that. So take the length of your training data model to compute your final. So once this is done, and then one is actually start the training process for your CNN. We have actually set it for 10 pods. Okay. So this might take time depending on the kind of GPU that you use. But I think all of us are using G4 GPUs on board. So let's see how fast it goes.
I tell you very lively. I won't make the direction. Try not to move the keyboard.
We also look at the loss and gradually increasing. That is what we want, especially. We want to reduce the amount of loss in the end. What we do is Alright, so the training pipeline is completed in my machine over here. So what I want to do is I'll just save the last best model that is training, and you can save that as a file, and we'll use that to perform inference. Okay, so in PyTorch itself there is a function over here called save, okay, and this component also actually holds the complete dictionary, as in the weights in which the final weights arrive in the training, okay, and this actually holds that information. Okay, so you're using that to encode it into a .pdh file, and you can use that to perform inference. Okay. So we do that, and I'll just leave it as last test model. And this actually holds the weights for the final model. First, what we want to do is we'll quickly load that and visualize that as a convolution matrix. Okay. So let's do that. So what we do is we take model.load and you know the state that you just exported. Okay. So you can do this. And we use the option load rate, where we pass the last best model. What you see. So you're loading the last best model. And now it's very important that previously we had a model in the training, okay, so which means it allows the computation rates completely. So here we use the model on the validation model, because now we completed the training pipeline and you want to use this model for inference. Okay. So you do model for example. And what I'll also do is have a list for all the predictions as well as a list for all the labels so that you can plot the condition labels. Right? So I'll use this here. Right. And now we'll actually do something similar to what we did in the training of neurons. Okay. And what we do is we can use PyTorch's inbuilt node tagging method over here. Okay. You pass your inputs. So for each image that you have in hand, your labels. And in this case, we take the test node, not the training node. So use the test node here. And again, you want to offer this task to the GPU. Right? So what you do is images and labels. Pass the images to device as well as the labels. And of course, you want our list to pass. And you want to pass the images. So it's doing this integrating capture. So what we will do is that we will use the images and the labels to labels. Okay. And we are also getting the predictions done from the model. Okay. And the model, what happens is we have different classes. Okay. We use these predictions that using a forward pass method. Okay. And that can be compared using downloads to visualize that in the form of the dimensions. Okay. So we'll just do only that. Because all these tasks can also be operated to CPU, especially when you try to do modifications using power. And if you decide whether you want to offload those tasks to GPU or CPU. So, what we do is now you have to predict models, right? And you can do a max function and pass your outputs. And what you also do is you can extend your predictions as well as your labels to it. So when you look at something like this, yes, you can extend. And these are the predicted components that you get from the outputs from the model. Then using that to get into a compile. I do the same thing for the labels. Operating is tasked to the CPU because you might not require GPU. It's not that any other task. Right, that's it. So, this guy probably 2 or 3 more lines to show the confusion areas and data. Right. So let's instantiate the confusion areas. And we can use that from C1's confusion areas methods. And what I want to do is pass the all labels, which are belong to tables, versus the predictions that we have from the model. Okay. And I want to pass the table here. It is to a real data frame. If I and we also define the size of the picture. We don't want a very large graphs. And if I also want to bring the C1's key map function to one way on the confusion details to check how it works. And here is where you pass the confusion areas. And also you want to show applications. So you enable that and also your format. These are the convolutions. And what your x and y axis, right? So just define that from predicted versus true. Right? So you need to be the x axis. We actually show the predictions. And on the other hand, the y axis will show the truth. And just period of show you display. Here is node state. So here we also have the dimension matrix screen, which actually shows how well your kind of predicts these values based on the predictions. Right? So how to use this? So you have the ground rule, so we have 0, and these are the so it's checking how many times, how many images you are actually classified for that specific comparison. And this is usually a good sign because you might want to see our zeros and very low values over here around this parallel rate. And you want really good high number over here to know that you have the best possible predictions from the model. So there is this part. in a pretty training spot. So in a case of writing, some of these functions, it really makes sense to read additional documentation to also look at what else these methods can be utilized. Right? And PyTorch is very well implemented, especially after TensorFlow, because of its very research and development use cases. Okay. So if you're actually developing deep learning models, then there are two libraries which are really great at that. So first we have your TensorFlow from Google. Okay. Especially if you want to build models at scale. Okay. So for example, if you want to build models, let's say streaming, right, and if you want to serve millions of people, then you would use TensorFlow because it has native methods for deployment and scaling the use cases. But on the other hand, if you are really core research and development, PyTorch is really good because you can do fast prototyping. You just saw that within, let's say, a little bit less than an hour, you were able to build a strong pipeline, which would give you an understanding of what the various components required to set up a pipeline, right from the raw data to the final collection. So, but as a beginner, it's good to start with TensorFlow because it's even more well documented compared to PyTorch. Right? So you can use it for probably 1 or 2 years and then move to PyTorch when you are into research later in university. Right, so with that, I actually have arrived to the end of my talk today. I actually have a feedback form. If you felt that anything over here would be improved, or you like something, or you dislike something, please feel free to give me let me know. And on the other hand, if there are any projects that you guys are working on, and let's say you're stuck somewhere, you're also looking for different use cases or problem statements or stuff like that, you can also type that into this. And we can also do a Q&A session where you can send me questions, and I will definitely email you back with responses, as well as if you want specific research papers, I can recommend you specific research papers for your for that specific problems. I can link you to that. Okay. So in the interest of time, I also learned from the organizers that you guys have exams. So I try to keep it as short as possible. But on the other hand, whatever you send, if it actually has a question or a query, I will reply with an email. So just drop in your email so that I can reach back to you. So everyone scan this. It's a very short. So thank you very much for being part of this lecture and for giving your valuable time today for this lecture, as well as even though you guys are going to receive your exams, I'm happy to see all of you here to spend time with me to learn something which you've done so far, as well as probably something which you've not done so far, or just understood something, or you also got an extension of what you already know. So all these three things were able to satisfy. So if you want to reach out to me, you can Google my name and reach out on any social media. I'll be happy to connect discuss anything if required. With that, thank you very much, and all the very best for the exams.
Thank you so much for taking your time and coming here and explaining to us essentially how CNN works. I'm sure it will be useful for everyone here in the or in the future when they work on problems. And we also want to thank everyone for showing up to this Google Doc. I'm sure you guys will find this useful. And this is also going to be something that CIS will hopefully do more regularly. So keep an eye out for more events that we gather more keyword features, more hands-on stuff, and some other things that we will be doing soon. So keep a look out. So that's it. Thanks for coming.